As Sonal was pointing out, I'll go over some of the basics of the baseline protocol, particularly around some of the core components that we've introduced with help from the main members of the community, predominantly from Provide and Consensus, and some of our work as we came along to open source or make this baseline project go into public domain. Essentially, I'm not going to go over some of the motivations, which I'm sure that most of you are aware of, but just as a quick roundup, some of the main considerations for baseline is how do enterprises communicate with each other, any form of inter-business communication or any form of logical interpolation or any form of synchronization for that matter on data, on process, or any form of business logic that enterprises deal with on a day-to-day basis with their other counterparties. So with that being said, some of the key considerations are around security to make sure that the data that any of the enterprise systems use to interact with the mainnet, that data itself doesn't leave the legacy systems, and any form of data interchange or transformations, etc., remain hidden. While doing so, it is significantly important to make sure that the information of the various counterparties or the various parties on this baseline protocol are the information that is being shared is consistent. And the way this consistency can be maintained is by using some form of state accumulators or some mannerism in which the state of data that any party commits or any party attests to is consistent with any other party that is a consumer of the data or an attester of the data or a validator of the data for that matter. So in that sense, we need to, one of the main considerations with data consistency is the compatibility with multiple data systems. Different organizations may have different types of data systems or database technologies or even data governance considerations or data architecture paradigms. But being aware of all of those aspects or all of those variations or variabilities, the main consideration is making sure that the data across the various types of models is consistent across all the enterprises. And in doing so, we want to use mainnet as the primary source of truth or a common reference frame by which all different parties can more or less subscribe to the various changes that are happening in the data or the various state changes that might impact the primary blockchain itself. So we do so by introducing a set of smart contracts to verify data consistency while keeping the data hidden. One of the other consideration is that with the changing nature of the mainnet, with various folks coming up, or with the folks that have come up in the last 2 years even, with Byzantine and London hard fork, and also with the new types of pre-compiles getting added to enable different form of signature mechanisms or even zero-knowledge proof-based proofing or verification mechanisms are continuously changing or continuously being upgraded with the introduction of new EIPs and so on. So it's important that as we are lining up things to use mainnet as a common reference frame of data, it also needs to be extensible to various changing privacy techniques. And finally, scalability is also of main importance, as we know that there have been numerous issues, or rather numerous quote-unquote concerns with the rising gas fees of conducting any business or any transactions on the mainnet. It is important that for scale, not only is it important to be able to commit any of the private elements or private data or private logic to the mainnet, but it is also important that it needs to be extended to many other private states, and the ability to compose multiple proofs, given the nature of the zero-knowledge proof that is embedded with any verification of a business logic or a business data or data synchronization for that matter. it's important to compose these proofs and conduct efficient verification. So just wanted to give a basic roundup of why and how we came about in terms of building the baseline stack, or coming up with or working with the folks like Andreas and Kyle to come up with standards as well in this case. So that I'll just go forward into some of the primary baseline components. As I'm going over these, I'll switch to the repo as well in the interim to walk through some of the elements, or rather the library components that could be used, or that were used rather, in their various reference implementations as well. So starting from the top, we have these five packages or these five components are some of the critical components of the baseline stack. It starts off with API, which is around creating this is RESTful interface, enabling solution providers or like solution adopters of the baseline protocol, or any organizations of the baseline protocol as they're adopting the standard. It's important that API acts as a mechanism for enabling either REST-based endpoints or any form of microservice-enabled endpoints for businesses or parties to conduct business with each other. So I'll quickly switch to the repo itself. So we have in the baseline stack, all the various services or the components are structured under the baseline core. And particularly under API, we have a TypeScript form of an interface definition, where you could see that we have various interfaces to essentially maintain or connect to an RPC, maintain an RPC connection to the mainnet. And there are a bunch of other interfaces as well. So for example, here, one of the main interfaces, the baseline RPC, we have a few methods to be able to get the commit of any object or data that is getting attested or verified and then put into a Merkle tree. I'll talk about the overall business process as to where a Merkle tree comes in, but the idea is that this RPC interface, or this baseline RPC interface, essentially contains a list of methods to track and follow the state changes that are happening on a Merkle tree. So the idea is that as different, as say, for example, any given organization is communicating a piece of message or any form of data packet to other organizations. As we go into the details of how we do so, I'll just cover at the surface what these methods do. The idea is that when we are communicating, or when organization A is communicating with organization B about any business document or any business logic or any form of data structure, because we use zero-knowledge proofs and privacy-baked elements, it is important that we don't commit, or we don't send the message, or we don't commit the message directly to any smart contract, which is publicly, which is by means of which participants or folks on the mainnet can access the state changes itself directly. But we use a Merkleization concept or an accumulator concept, where we push the hashes of any of the data elements that we would like to communicate from between one organization to another directly into a Merkle tree, where each root or each leaf of the Merkle tree corresponds to a hash of the data that is communicated between the parties. And the hash itself is embedded with other properties around zero-knowledge proofs as well, which I'll go into in a few moments. And these set of methods essentially help in being able to getting the latest root of the Merkle tree, or getting a proof given a particular leaf, or tracking a particular leaf, or even verifying whether or not a particular leaf is a part of a Merkle tree. So essentially, this entire set of baseline RPC methods provides an ability to store store hashes in the Merkle tree, both on-chain, but also maintain a parallel collection in your local MongoDB or rather, when I say local MongoDB, a part of the persistence in the baseline protocol, which I'll go to, which is one of the next elements. So the idea is that each hash that is getting stored on the blockchain also needs to have a representative structure or storage on your local databases as well when it comes to participants. We also have some of the standard ones for connecting to a blockchain service here, like broadcasting a transaction, fetching transaction receipts, or even signing any payload before sending any message. Then we have the registry interface. This is where this is the interaction with the organization registry smart contract. So the idea is that when we are interacting with various parties on the mainnet, it is important that we need to be able to have some form of an identification and also an enablement or a provision for, say, for example, different KYC providers or email providers to be able to detect or identify who the counterparty is or identify who the various organizations are. So to that extent, we have various methods which are essentially behind the scenes. You could think of each of the implementations of these methods to interact with the smart contract using RPC methods. So to that extent, we have work group functionalities to create work groups, to fetch the various work groups, the details, the organizations under the work groups, and so on. Similarly, we have a vault, which is to enable any of the users or any of the protocol users, or baseline protocol users or adopters, to be able to have some form of secure storage of the keys or the private keys that are being used in the context of baseline. The traditional keys that most of us know are of, say, any form of secrets that are used to sign any transactions in general on Ethereum, which is your standard Ethereum public key, private key pair. So the vault acts as an enabler for storing such private keys. But as we go forward, we'll notice that there is some elements of privacy as well, especially when it comes to ZKP. We use special form of signatures to ensure that parties signing a certain message, their identity is hidden under zero knowledge proofs. And to be able to do so, you need some special curves like the form of EDDSA curves, and also BLS type signatures to be used as part of signing a given message. So apart from traditional private keys that we nominally use for signing any transactions to interact with the mainnet, the vault is also designed or rather facilitated to store other types of private keys as well, like the private keys that are needed for BLS signatures, or the private keys, or even the curves that itself that are used to construct the BLS signatures and so on. So in that sense, API acts as a way to interact with the blockchain, way to interact with secure key storage, and finally interact with the smart contracts that are deployed on the mainnet. The next one we'll go into is the contracts. So as part of contracts, some of the primary contracts that we have are around setting up work groups. Obviously, these set of smart contracts are just the base ones, and any extensions are welcome and any extensions are possible here. But when we came up with this architecture originally, the idea was that we want an ability for different organizations to be able to identify each other, who they are working with, and also the ability to ensure that these organizations are valid and identifiable organizations. So the notion we came up with was that various organizations, there can be many organizations which are effectively using the mainnet and especially interacting with, say, the baseline protocol stack. but different organizations have different business imperatives, and they have different working relationships with different other types of organizations. So for example, in a supply chain use case, you might have buyers, suppliers, manufacturers, and transporters. And each of them may have each of them could be assumed to be a part of the same working group. But on the same extent, each of these entities, like a buyer, supplier, or a distributor, or a transportation agency, may have their own sub-service line or subsidiaries, or even downstream business partners that they might be doing business with. Like a transportation agency, for example, may be in turn working with, say, a local logistics company or a warehousing company to be able to store goods upon receipt of any manufacturing goods, and to be able to ship them over to the intended recipients, like the intended buyers itself. So to that extent, again, this work group that transportation agency may have may be very local, so to speak, in terms of business imperatives for the transportation agency. And in a similar manner, a buyer may, or a different participant on the ecosystem may, or in this group, may have their own downstream providers that they deal with, their own tier 2 suppliers or tier 2 manufacturers, and so on. So regardless of all this, what we came up with was that if there was an ability for different organizations to identify themselves and form working groups so that they can uniquely identify which working group they're a part of, and at the same point, to the same token, we have organizations being added to the working group, or removed from the working group, or moved from one working group to another. So the idea is that we would want a standard, or we would want a good EIP that we could use for representing organizations and their work groups. And not just that, we also want to make sure that the work group or the set of contracts, or set of, say, the Merkle tree contracts or the shielding contracts that are needed for zero knowledge proofing, they are also custom to each working group. So a working group, for example, a working group that consists of, say, hypothetically just a supplier and buyer, maybe could be rather attuned to just verifying, say, proofs of any documents that are being shared around, say the agreements that are agreed upon, like in terms of the goods that need to be procured, or say the purchase orders or invoices, etc. So each of them each of them has a corresponding, say, functionality in the Shield contract to, say, verify an MSA, or verify a purchase order, or verify an invoice. Now, if you take, for example, a different working group, say if you take a transportation agency and, say, a logistics company, they may have their own shipping contracts and their own delivery terms and so on and so forth. So to be able to verify the shipping contract details, or to ensure the data integrity of the shipping contract between, say, a transportation agency and a local warehousing agency or a logistics company, they may have their own verifications of verifying a shipping notice, or verifying a shipping contract, or verifying the logistics contract, and so on. So to that extent, it's key that organization registry as such not only has a facility to create different working groups, but you're also able to register different types of interfaces. So a Shield interface is an example in this case, where a Shield contract or a Shield and a verifier as a combination can have different interfaces or different definitions based on how they're interacting with the Merkle tree itself. So to that extent, organization registry also has functionality to register the various interfaces. So I'll just quickly switch to the baseline contracts. So this is the example of this is the implementation of the org registry. And in here, you can see that we have an ability to register organizations, which is where we capture all the important details of a given organization, like their Ethereum address, a unique name, which could be an ENS domain as well for that matter. Then you also have the messaging endpoint. And this is one of the older artifacts where we were using or we were relying on using Whisper for inter-party communication. But as I go into messaging next, we'll go into particularly the NATS key here. So this Whisper key is more of an indicator of the messaging endpoint, or sorry, the key that is needed to identify your counterparty when it comes to sending private messages. Then we also have a ZKP public key to indicate an organization's signature, main signature key. So in the case of baseline, and in particularly in the case of sending secure messages across, one of the key aspect is the type of signature mechanism that is being used is that particular signature mechanism's public key is what we would want to capture over here as part of the registry of the organization. So this functionality walks through or provides an ability to register organizations, not much different, very similar to many of the other naming registry or naming or organization registry or name registry contracts that folks must have seen. But we also have another method where we are essentially registering interfaces. So different types of interfaces or different types of implementations of a given interface can be used by the working group organizations. So we have a token address in case there is a standard token. It could be a generalized token factory, which can be used to create multiple tokens, or it could be something like an ERC 1155, which could be used for batch minting, or any of those token factories or token standards that could be leveraged. So this, the interfaces, so the registration of interfaces includes a token address, which is a representative of a token interface, a shield address, which is representative of a shield interface, and a verifier address, which is representative of a verifier interface. And the main aspect over here is that when we chose to implement this, we used the standard for ERC 1820, which is a standard that was published to the Ethereum mainnet, and also which is one of the EIPs out there, which was proposed about 3 years ago, where it followed on these principles to ensure that the principles of making sure that different interfaces can be registered in one sort of global registry. So the idea is that when we are using ERC 1820, it acts as a factory of factories or an interface of interfaces. So it, in one of John's famous words, it's like a corporate phone book of sorts, where you can have you can use ERC 1820 as a registry of registries, so that you can have various types of organization registries into their work groups or shields or verifiers, etc. But all of them can be dependent, or all of them can be registered with one parent ERC 1820. So this is where the usage of ERC 1820 comes into picture. So that's about the contracts. Then we go into messaging. Messaging is essentially a way to send private messages or encrypted messages from one organization to another. These encrypted messages are essentially needed to be able to communicate any private information, or rather, particularly the information that is needed to verify a zero knowledge proof, which is what we'll go into next. But at the core level, the messaging is like a interface or an enabler for, it's a library containing a set of interfaces to TypeScript-based interfaces to interact or with any form of messaging providers. So in the repo itself, we have in the repo itself we have two types of messaging providers. You could see one of the main ones which we use now is called NATS. And we see that as part of this interface, one second. Okay, so you'd see that in this interface, we have a bunch of standard methods to be able to connect to a NATS endpoint, or rather make a connection with a NATS service, disconnect from the NATS service, and also publish or subscribe to messages that are being used, so that are being sent across between one party and another on the NATS interface itself. So this, in short, this this particular package deals with enabling interfaces or creating standard methods or standard functionalities to be able to connect to NATS, and similarly to be able to connect to Whisper as well. Although we don't use Whisper much these days in lieu of NATS. For that matter, the idea is that this could be extended to other types of messaging providers as well. In the past, we did come across several questions around the ability to add somewhat more beefy messaging providers like Kafka or RabbitMQ. But to that extent, we used a more lightweight protocol like NATS. With that being said, it is obviously open for developers to extend this messaging interface to not just include NATS and Whisper, but you can go ahead and create other forms of interfaces as well. So the main idea is that each of these packages acts as a standalone NPM library, which could be used to set up a container, or rather used to be set up your local in your organizations or your custom legacy systems, microservices, or say cloud services, or even say on-prem services for that matter. Persistence is intended to indicate any form of data storage. I won't go too much into the details, but in short, the idea is that persistence acts as a way for integrating with your local data systems. In the case of baseline and in the case of some of the BRIs, we'll notice that in many a time this persistence is referring to the DB technologies like Mongo or PostgreSQL. But in that manner, I think you could say that even the integrators for SAP or Excel or any other connectors that are being developed would be a good place for them to reside from a standard point of view, or from a self-contained component point of view under persistence. So finally, we have privacy, which is pretty much the main piece of, or the main engine behind hiding critical or business critical information or business critical logic, and which is where we use zero knowledge proofs. So to start off, I'll just show you quickly the interface, and then I'll go into some more detail of how we use zero knowledge proofs for securing messages or hiding private information. So, so as you've seen with, in general, the way the core of the baseline is structured is that it follows a standard of using TypeScript-based interfaces, and this was one of the main folks who has championed over this is Kyle, who has spent a good amount of effort in our initial days to ensure that the stack has a standard interface pattern, and so that each library or each interface can be thought of as a provider of various types of libraries or various types of connections. So in API, we had seen like one type of provision or like one type of provider. The interface that we had seen in API had like various methods for RPC connections or for interacting with the smart contracts and so on. But when it comes to the implementation, there can be many ways in which that could be implemented or virtualized. So for example, one could use, in the case of RPC, a standard like say Ethos.js or Web3 to connect, or in some cases, some organizations have created their own CLI methods. So each such implementation or virtualization of the base interface can be thought of as a provider. And to that extent, you'll notice that across the various packages, this notion of having a provider as an implementer or as an implementation of these interfaces or of these interface definitions that are provided in the definition of each of these packages could be extended. So to that extent, even in the case of privacy, we have a ZK circuit provider. We have an ability to get the compilation artifacts, the trusted setup artifacts, and also the providing the generating the proofs itself. So that being said, so privacy in that extent has enablers or abilities to be able to interact with some existing ZK SNARK providers. When we are talking about ZK SNARK providers, in this case, we are referring to the various libraries. We started off with using Socrates, and in the weeks and months or the year that followed, we have we started also looking into NARC, which is another form of which is another ZK SNARK library, which is written in Go and which has other elements of generating proofs or verifying proofs aside from Socrates. So in the case of Socrates, I think there were some of the Groth 16 and GM17 were some of the standard ones used. But in the case of NARC, I think you could use some other proving and verification systems as well. So I'll just give a quick walkthrough of let me just go into the privacy management itself as to how it works. And then I'll wrap up this discussion with giving an example of how a document that is exchanged between two parties can be using the baseline protocol stack, and how the messaging and the consistency of information and privacy is maintained while using the mainnet. So before doing that, I'll just quickly dial down into the privacy management piece. Here we are talking about how any given participant or when you have two given participants like Alice and Bob on the baseline protocol stack, or leveraging the baseline protocol, assuming that all of them or both Alice and Bob are able to set up this structure locally to essentially have various microservices or various services on-prem or cloud or otherwise. Once they are set up with all these enablers or all these interfaces. So essentially what that means is you're able to make the various components under API, smart contracts, messaging, and so on available as services that you can interact with locally. So given, assuming that both Alice and Bob have that base stack set up, the idea is that in the case of ZK SNARKs, usually you have an ability to create private proofs, or rather proofs of any form of a business logic or a business logic statement. So this aspect, or this is done using what you call as circuits, which are essentially R1CS, or they're a constraint-based system-based circuits. So similar to Boolean circuits or like Boolean gates, you have arithmetic circuits, and that's what these circuits refer to. And we don't need to write these arithmetic circuits directly in that language, but you have other DSLs, like in the case of Socrates, there is their own custom DSL by which you can write your own circuits. The idea is that each circuit essentially represents a self-contained functional component of a proof, or rather to verify or validate a logical statement. So for example, in the case of baseline circuit, we have we embed these types of proofs. So we have a proof of knowledge of a document hash, where the idea is that the hash the hash of the document or the data object that needs to be secured while communicating. The assertion that we have is making sure that whatever the input document is, whatever input document hash is, that matches with the document hash as it was hashed within the circuit itself. So independent hashing versus within the circuit hashing is where is what this proof indicates, or this assertion tends to prove. Similarly, we have a proof of knowledge of signature, which is where we ensure that whether or not the buyer and supplier, or for example, Alice and Bob, their signatures are verified. And in doing so, the verification is behind the scenes is using a library circuit that which essentially proves whether or not points are on an EDDSA curve. So because EDDSA based signature mechanism is used, this particular proof of knowledge of signature encompasses the verification of a signature by a certain buyer or a supplier or any of those parties, and it's important that those are satisfied. And finally, we have the proof of membership of a hash in a Merkle tree, where what we make sure is that when we are inserting any leaf into a Merkle tree, say for example, a hash is determined and that hash needs to be set into the Merkle tree. The important point over here is to make sure that the root that gets changed upon every time a hash is inserted into a Merkle tree, that root is calculated correctly, and that the root itself is representative of the hash of the actual document. So this the circuit itself, you should be able to find it in the baseline document.zoc, which goes into a little more details of how this membership proof is set. For set membership proof is identified. Similarly, how the various how the EDDSA based signature mechanism is used to verify signatures, and hashing, where we're using the standard SHA based hashing to ensure, or sorry, to check or to make an assert that the input document is the same as the hash that you compute within the circuit. So this, in the case of privacy management, when Alice intends to interact with Bob, they would take a circuit such as the one we just saw, compile it, set it up, and publish those artifacts. And using those artifacts, you can deploy the verifier smart contract. So then the smart contracts, the verifier smart contract contains a functionality to verify any proof that is being submitted can be verified under zero knowledge. And what it means under zero knowledge is that verifier uses a library, a pairing curve library called BN256, and that is what is used to verify whether or not a proof is legitimate, or rather a proof is a point on that parallel elliptic curve. So the verifier interface is essentially used to, the verifier smart contract is essentially used to verify and verify any form of zero knowledge proof. So the idea is that Alice at the beginning, or any particular operator can stand to publish the circuit itself, and at runtime, anyone using that particular circuit, in this case, say for example, Alice is using that same circuit to verify, or rather to generate a proof. That proof can be used by Bob at any given point to verify whether or not that proof contains that proof is legitimate. So basically ensures that the proof is a valid hash of a valid document that was shared between Alice and Bob. So with that, I'll just round up this business flow upflow document. So you have, say, party A and party B who are using the baseline stack. It starts off with party A generating a commitment, which is essentially generating a hash, signing that particular hash. And this signing is done using a special signature mechanism like the EDDSA. And one form of EDDSA we have been using in this, or at least that has been originally published to the baseline stack, was the baby jib curve. But to that extent, any other form of signatures also can be used. So we send that signed commitment over to party B. And then when party B receives that signed commitment, they re-sign that commitment and then send back the document with the second signature, or which is signed again, back to party A. And at this point, party A can generate a proof which essentially contains all those three methods that we spoke about to ensure that the hash is correct and to ensure that both parties have signed off that document and verifying that particular signature under this proof. And finally, inserting that particular hash as a leaf in a Bunkel tree, both that is stored locally. So the proof itself contains the membership of a particular leaf in a Merkle tree. And then that particular proof is verified by calling the shield contract. And this may be optional. If party A does not need to verify the proof, they can still verify the proof locally without making an interaction with the shield contract. But this is just for posterity. It is shown that both anyone can verify this proof. And then after verification of such a proof is when the proof is being sent. And once the proof is sent and as a part of party B as well, either party A or party B can call the shield contract to ensure that the proof is valid. So that's essentially a high-level overview of how the business workflow works in the context of the various components of the baseline stack.